Well, here is a quick video on the assignment questions on chapter 19 and 20. I'm planning to do 3 questions. The first one here is coming up. Because these 3 questions may take up a lot of time. And so I'm just, and this is done quickly, so I have a printout which I am posting. I'm trying to give a quick explanation. Hope that is useful for you. Okay, so the first question talks about, I hope you can read it, 2.7 moles of helium gas at 252 Kelvin are kept in a container. The temperature of the gas is increased to 450 Kelvin at constant volume. How much heat was transferred? Okay, so this is direct because you know that you have to just multiply the number of moles with the specific heat capacity at constant volume times the change in temperature. That'll give you the quantity of heat absorbed. And then from the first law of thermodynamics, the change in internal energy is Q plus W. Because remember that the sign for the work changes because of the work done on the system, which is taken as negative. So that's why you have a positive, and then you understand that because there is no change in volume, the work done will be, the change in internal energy will be the same as the heat absorbed. So that's how you do that part. Then the B part, the C part says, suppose the temperature of the gas is increased from 252 Kelvin to 450 Kelvin at constant pressure, how much heat is transferred? So now it's talking about constant pressure. So in this case, you have the number of moles again, but you have the CP, which is the molar specific heat at constant pressure. So use that and do it as we did before. So that's not a big difference. That is the same thing. So that will give you the answer. And but in this case, the change in internal energy, you're asked to find the work done actually. D says how much work is done on the gas. So once again, we use the first law of thermodynamics, which is here. Change in internal energy is Q plus the work. And then rearrange to get the work, which is change in internal energy minus Q2. So you have the change in internal energy, which is the same as in the last case when you heated it at constant volume. That's very important. And then you take away the work done in this case to give you the answer. So that's how it's done. Now this question talks about an ice maker inside a refrigerator that makes ice cubes at 0 degrees Celsius from water that is at 15.7 degrees Celsius when it first enters the ice maker. This machine is rated at 214 watts and has a 3.26 coefficient of performance. What is the maximum amount of ice it can produce in a 24-hour period without any interruption or stoppage? Okay, and so the specific heat of water is given, latent heat of fusion of ice is given. So you're interested, we are trying to find the amount of ice made in one day. So we have to find out how much work has to be done to make that ice. And work is power multiplied by time, okay? So the power is given here, 214, and we need the time in seconds, so that's why you have 24 hours times 3600 seconds in an hour, so that gives you the total work. Once you get the total work, you have to use the coefficient of performance, which is QC by work, and then from there you find out the quantity of heat that is to be absorbed from the cold sink. So you get that using this formula, work times COP. And once you get that, you really have to find the amount of heat required, because first you have to cool the water to 0 degrees Celsius. So that is given by MC delta T. And then you have to change the water into ice, which is given by mass times latent heat. After you find both, you add them up, and that's done here in one step. And then you can calculate the mass of ice because you know QC, right? And in two ways. Put them equal to each other, and you get the answer as 151 kilogram. Now this question asks you to find the total change in the internal energy of a gas that is subjected to the following two-step process. First step, the gas is made to go through isochoric heating, which means the volume is constant until 5,260 joules of heat is transferred into the gas. Its pressure is given. In the second step, it's now subjected to isobaric compression, which means the pressure is kept constant and the volume decreases by, that much. So that's a change in volume, note that. And 1,210 joules of heat is transferred out of the gas. What is the total change in internal energy of the gas? So we go straight to the first law of thermodynamics. Change in internal energy is Q plus work, where again work is done on the system. That's why you have that negative changing into a positive there. And work done is, you see, given as negative P delta V. So, and you know that during an isochoric process, the work done is actually zero. That means the change in internal energy in the first process is just the amount of heat that enters, which is 5,260, right? But when you come to the isobaric process, we use the formula for work, which is pressure multiplied by the change in volume, which gives you that work. And so now, because you get the work and you also have the amount of heat that's transferred out of the gas right there, use both in the first law of thermodynamics to find the change in internal energy right here, which is negative 1210 joules. Why negative? Because heat is leaving the system, plus the work. So that gives you the total change in internal energy. Finally, you take the sum of the two changes, you get the net change in the internal energies during the two-step process. So, like I said, this was a quick video, and I hope it's helping you out to finish this assignment on time. Thank you.